Hello guys, good morning. Good morning to all of you. How are you all? Good morning to all of you. How are you all? Is everything all right? Good morning, Morley. Today we are going to start perturbation theory. Perturbation theory, we have time independent perturbation theory and time dependent perturbation theory. And within time independent perturbation theory, there are two types: non-degenerate perturbation theory and degenerate perturbation theory. So we'll start with time independent non-degenerate perturbation theory. Okay. So let us explore the concept of perturbation. Everything is all right now. Can we start? Where is Harry, Karthik and others? Look, let us start the discussion of perturbation theory. Till now, whatever systems we have considered, we considered some standard potentials, right? Standard potentials like particle in a box, that is one potential. Harmonic oscillator, there is another potential, and different potential we have tried and put the potential into the Schrodinger equations, and we got the exact solution. By putting the standard solution, standard potential, and putting it into the Schrodinger equation, we have got exact solution, right? So we have mainly used this equation H psi is equals to E psi, right? Or okay, so this was the case. Now in perturbation theory, what is different? In perturbation theory, the potential are not exact or standard potential. It is slightly varying. Let's say we have the harmonic oscillator potential. For that harmonic oscillator potential, we know the exact solution, right? Now let's say if some additive term or some other term is added with the potential, then the Hamiltonian will change and we may not get the exact solution. So for those cases, the perturbation approach is useful. So this is for the standard potential. So for the standard potential, we get the exact solution and we get exact Hamiltonian H0. Okay, this is the exact Hamiltonian. Now if some perturbation is there, so perturbation means standard potential plus some perturbation. So you can say small deviation from the standard potential plus perturbation. For this kind of case, your exact Hamiltonian is changed. Okay, so it then have two components, one from the exact Hamiltonian, let's say half kx square plus some, let's say lambda x or something, plus the perturbed Hamiltonian, and as a result of that the solution will also change. Okay, we will not get the exact solution will change. Now let's say by using H0 psi is equals to E psi, we have got the exact solutions. So we get, let's say, the energy eigenvalues and eigenstates. So when we write En0 means this is the for a standard potential case without perturbation. Okay, unperturbed. This shows unperturbed energy. Unperturbed, when the perturbation has not been applied. This 0 denotes the zeroth order of perturbation, means unperturbed. Similarly, you can write psi n 0. Now, when we have this perturbation, then the energy is changed. New energy will be the unperturbed energy plus the correction due to perturbation. So, the correction can be done in different orders. The greatest correction may be this one, so the first order correction, maybe some other corrections and a second order correction and so on. Okay, in a similar fashion, this psi n will also be changed, psi n 0 plus, let us say, the first order correction in the wave function, second order correction in the wave function and so on. Okay, is the basic thing is clear. We will talk about the theory in detail, but this, for the time being, this is the basic thing. Is it clear? If I give you a practical example, let us say we know that 64 is a perfect square, right? So, you know the square root of it, 8. So, it is like if you are given 65, then what will be the square root? So, from the knowledge of this, we will try to find out the square root of 65. It is like that. You know the exact Hamiltonian, you know the solution. Now, if this is little bit deviated, some extra added term is there, then what kind of change you will expect in the energy eigenvalue and eigenfunction. This is the core idea of the perturbation theory. Got it, Murli? So, let us start the first case, that is time independent perturbation theory. Non-degenerate. So, you know the meaning of non-degenerate, right? External perturbed or internally perturbed by itself. No, some external influence. Internally, how can you perturb? Wait a moment. Okay, so let's focus on time independent perturbation theory non-degenerate. So as I told you that here the new Hamiltonian will be the sum of the exact Hamiltonian plus the perturbation. Okay, this is your exact Hamiltonian and this is the perturbation. Obviously it is basically some small amount of energy. Okay, so you can imagine it some kind of small influence. The way I have shown you 64 and 65, you can imagine it in this way. Lambda much less than 1. So this contribution is very much negligible. So you know the exact solution for the exact Hamiltonian H naught. Okay. Is it fine, Murli? Audio video, actually it got disturbed for a moment. Look, the exact Hamiltonian, let's say this is the exact wave function. This is equals to En 0 phi n. So this is the Schrodinger equation. H0 can be solved exactly. Now we take the modified Hamiltonian after the perturbation effect, H0 plus. So this perturbation, it's a energy, so we can write it in terms of lambda times W. Okay, some constant times W. Lambda is much less than 1. So H0 plus lambda W times, let's say psi n. Phi n is the exact wave function, psi n is the new wave function in the new Hamiltonian. This will be equals to En psi n. En is the modified energy. Where this En is nothing but En 0. This is the unperturbed energy plus lambda time En 1. This is the energy with the first order correction plus lambda square En 2 plus so on. Okay, and the new wave function can be written as the unperturbed wave function phi n plus lambda times first order correction in the wave function plus lambda square second order correction in the wave function and so on. Now our task is to calculate these energy corrections. Mainly in your examination they ask you about the first order correction in energy, second order correction in energy and first order correction in wave function. Only these three terms they ask you to calculate in the examination. So let's calculate. Let's give the formula for both, for all of them. First order correction in energy. First order correction in energy, En1. Okay, what is the first order correction in energy? En1, this can be written as phi n W phi n. Okay, so lambda into W is Hp. So by taking only the first order correction, you will get the energy En0, this is the unperturbed energy, plus the perturbation lambda times En1. So lambda times W is Hp. Okay, so you can write it phi n Hp phi n. Can I write it? This is the first order correction in energy. Let's talk about first order correction in eigenfunction, that is psi n1. What will be the first order correction in eigenfunction? So that will be psi n of 1, this is equals to sum over phi m W phi n divided by E n0 minus E m0 phi m not equals to n. You can see En0, this is the nth order, nth energy, nth state energy for the unperturbed case. Em0 means the mth state energy for the unperturbed case. So this is the first order correction in the eigenfunction psi n1. Now what you are left with? You are left with psi n En2, first second order correction in energy. So let's write that second order correction in energy. Denoted by En2. Look, second order correction in energy, En2, it is given by this formula, sum over m not equals to n. Look, only the difference will come here. Here it was only phi m W phi n, but here now it will be square, mod square, divided by En0 minus Em0, that will remain as it is, and this phi m will not be there, only this m not equals to n. Why? Because if m and n are equal, this denominator will become 0 and that will make this term divert. That is why m not equals to n. So if you add the second order correction, then how we can do? We have to write the first order correction En0. Okay, then you have to write lambda times the first order correction. Sometimes this is this exists as one term. Okay, lambda is somehow absorbed here, plus lambda square En2. If you write, let's say, HP here, instead of writing W, H, if you write HP here, so obviously this lambda will be absorbed, as you can see here. If we can write lambda into phi n W phi n, or we can write phi n HP phi n. So depending on you can write. If you are putting HP here, then there is no need to write lambda. So with the second order correction, this will be the energy. Obviously, this energy will give you better result than this. So the more and more correction term you will keep on adding, you will get more and more exact expression for energy. Understood? So this is an approximate method. Perturbation approach is an approximate approach. You will not get the exact energy. The way you used to get exact energies for exact Hamiltonian or standard potential, you will not get exact energy here, you will get an approximate value of the energy. This is how perturbation approach is different from the other approach where standard potentials are considered. Any question till now? This is a theory for the time independent degenerate, non-degenerate perturbation theory. Okay, let's solve this problem. If the perturbation H prime is equals to Ax, where A is a constant is added to the infinite square wave potential, the correction to the ground state energy to first order in A is. So you are given an infinite square wave potential like this. Infinite square wave potential, and as you can see it is from 0 to pi. Now, if the perturbation H prime is equals to Ax is added to the infinite square wave potential, then what will be the correction term? Look, you have to find out the correction to the ground state energy first order in A. So what you gonna do? You know what kind of energy you get in the ground state. Look, for the 1D infinite box of with a ground state wave function psi 0 of x is equals to square root of 2 by pi sin n pi x by a, so sin pi x by a, this one we know, right? Now, what is the first order correction in energy? First order correction to the ground state energy. Look at the formula. What was the formula? En1 phi n w phi n or phi n hp phi n. Okay. So let's put the value. So we can write E first order in the ground state. So E1 is the ground state. First order correction. So En E1 1. Understood? This is equals to which state? Psi 0. Perturbation is H prime here, psi 0. So this is what you need to calculate. So you know the technique how to do it. Integration 0 to pi psi 0 star H prime psi 0. So psi 0 star is square root of 2 by pi sin pi x by a. H prime is ax, psi 0 again 2 by pi sin pi x by a dx. So this is square root of 2 pi and square root of 2 pi, so 2 by pi 0 to pi, a is constant, so 2a by pi x sin square pi x by a dx. This is equals to, look, if I take this 2 inside, 2 sin square theta is equals to 1 minus cos 2 theta. So you are using that a by pi 0 to pi x into 2 sin square theta, so 1 minus cos 2 theta, so 2 pi x by a dx. Is it clear till now? Acha, here a is what? A is pi, na? So square root of 2 by pi sin x. If you put a equals to, because the width a is equals to pi, so it is sin x, na? So let's replace this. Cos 2x dx. So this can be written as a to pi, then 0 to pi x dx minus 0 to pi x cos 2x dx. The integration of the first term x square by 2. Now this is integration by parts we can use. So x into integration of cos 2x sin 2x by 2, limits from 0 to pi, minus, and this minus plus, and 1 minus will come from this integration. So that will give you minus 0 to pi sin 2x by 2 dx. A by pi, this is pi square by 2 minus this is sin pi 2 pi, so that is 0, and integration of sin, it is cos minus cos, minus minus plus half cos 2x by 2. So this is a by pi square by 2, and this is cos 2 pi is 1 minus cos 0, so that is 0. So this is nothing but a pi by 2. Okay, I think this would be plus now, minus minus plus, integration of cos is sine, and now here it will be plus minus. So which option is it matching with? Option A. So very simple thing. A particle of mass m naught and charge E oscillates along the x-axis in a one-dimensional harmonic potential with an angular frequency omega. If an electric field E is applied along the x-axis, what will be the first and second order correction to the energy of the nth state? Read the question carefully. You have a particle of mass m naught and charge E oscillates along the x-axis in a one-dimensional harmonic potential with angular frequency omega. If an electric field E is applied along the x-axis, this is the x-axis, let's say, and you have applied electric field E along the x-axis, then first order correction to the energy. Look, the perturbation which we are talking about, it is added with the exact Hamiltonian. Hamiltonian is what? It is basically unit of energy. So HP, from the dimensional equivalency of the dimensional analysis, HP must be energy. Here you are giving electric field, so you have to convert it into corresponding energy. Okay. So the potential energy, we want to calculate the perturbation. It is given in terms of electric field, but we have to convert it in terms of energy. So the potential energy due to the field E is, what will be this value? Minus P dot E. This is the formula of the potential energy, right? Because the charge E oscillating under this harmonic potential, so it will behave like a dipole. Okay, so minus P dot E, this will be the formula, and you see, we can imagine it in this way: dipole moment, what is what? Charge time the displacement. Here it is displacing along the x-axis, so it is like minus E times x. This is for the dipole moment, and they are along the same direction. So this, we can take it in this way. So this is minus EEX. So therefore the perturbation H prime is this one, minus EEX. Now this X has some important thing. You know what is X? We have done it in the case of harmonic oscillator, 1D harmonic oscillator chapter. Minus EE. X we can write in terms of the raising and lowering operator, square root of H cut by twice m omega was there. So twice, here m is m naught omega times A plus A dagger. So we have written the position as the position operator in this way. So what is the first order correction to energy in the nth state? So therefore the first order correction to energy of the nth state. So again, E n, nth state energy, first order correction 1. This is equals to, you know the formula, nth state. So n H prime n, this is what you need to calculate. So this is minus E times E square root of H cut by twice m naught omega n A plus A dagger n. And what is the value? You know it very well. What will be its value? Can you tell me? Murli? What is it? What will be its value? First order correction. Zero. Now the second order correction to energy. Energy of the nth state. Nth state correction in the to the second order. So you know the formula. M not equals to n h prime m mod square, then E n0 minus E m0. Now if you look at this term, so it is like n a m plus n a dagger m, isn't it? So if I just write it, let's take this term out. N h prime m. This is equals to how much? Minus e square root of h cut by twice m naught omega. Okay, n a plus a dagger m. Okay. Now this is simply minus e square root of h cut by twice m naught omega. First term n a m plus n a dagger m. Now you see which value of m will survive. Look, m can take all integral values because n means what? It starts from 0, 1, 2, 3 and so on. Ground state, first excited state, second excited state, third excited state and so on. This is the n value for the 1D harmonic oscillator potential case, right? So here the sum is being carried over m. Under only one condition, m and n cannot be same. So n and m, they cannot be same. What value of m you will choose here so that you get non-zero term? All the other term will give you zero term, right? Which values of m can give you non-zero terms? Understood my question? Let's say if you choose m is equals to n plus 2, then a will make it n plus 1, then it will be 0. Similarly, this will also be 0. But if you choose, let's say m is equals to n plus 1, if you choose m equals to n plus 1, then this lowering operator will make n plus 1 to n, and then it will be non-zero. This will be 0, but this will be non-zero. On the other hand, if you choose n is equals to n minus 1, then although this term will be 0, but this term n minus 1 will become n and this term will be non-zero. So here m can take all integral values, except n. Okay. And which are the non-vanishing term? Non-vanishing terms elements correspond to, if you choose m is equals to n plus 1, then the first term will be non-zero, and if you choose m is equals to n minus 1, the second term will be non-zero. So all other values of m will give you 0 result. N and m interchange in numerator of second order correction formula. No, this en0 minus en0, this is where the correction is being carried out, okay, nth state. So this will remain same, en0. Now this en0 will change. Let's say if they ask you to calculate in the second excited state, so this will be e20, okay, then m value cannot be e2, so e20 minus e10, maybe e20 minus e30, e20 minus e40, only e20 minus e20 will not be there, okay. Now let's say if you are if you are asked to calculate the correction in the, let's say, e3 state, so what will be the m value? You can go with e10, you can go with e20, but you will not be allowed to go with e30, you will go with e40. It is basically sum of this. So once you will take e10, whatever term will come, and here only e10 will be there, then plus other terms in place of em0 you will write e20, and so on. Numerator also, n will remain n when you choose. So the first term, the numerator will be, let's say you are calculating in the third state e30, okay, so this will be 3h prime 1, and square and all, everything will remain, and here also you will put the energy as required, plus next term will be 3, this n will remain fixed, okay, h prime 2 we can use, then square, obviously square and some constant is there. Next 3h prime, we cannot write m is equals to 3, m is not equals to n, so you will go for 4. So it will continue depending on the states. Understood? So what will be the value of en2? En2, as you can see, only for m is equals to n plus 1 and n minus 1, this is non-zero, otherwise it is 0. So en2 will be equals to, look, this is mod square of this thing, so this becomes e square epsilon square h cut by twice m naught omega, now square of this, okay. The first term is n a, let's say we put n plus 1, m is equals to n plus 1, mod square divided by e n0 minus e n plus 1 0 plus n a dagger n minus 1 mod square divided by e n0 minus e n minus 1 0. Did you get it? Look, in the first term n a n plus 1, another term will be there, n a dagger n plus 1, but that term is 0, that is why we have not written here. Similarly, when you put m is equals to n minus 1, there are two terms actually, n a dagger n minus 1 plus n a n minus 1. So n a n minus 1, that is 0, that is why we have not written here. So this is equals to as you can see, E square h cut by twice m naught omega. What is this term? This is as you can see, square root of n plus 1 and mod square divided by En0 minus En plus 1 0. So you can imagine it in this way. This is your En state, this is your En plus 1 and this is your En minus 1. This is the nth state, this is n plus 1th state, this is n minus 1th state. So what is the energy? You know it, n plus 1 plus half h cut omega. This is n plus half h cut omega. This is n minus 1 plus half h cut omega. The separation you can see, this is h cut omega. H cut omega. So En0 means this minus En plus 1. So this is obviously greater than this. So there will be a minus sign. So minus h cut omega plus this one will be square root of n square. En0 minus En minus 1 0. So this is plus h cut omega. And this is equals to, as you can see, this is n plus, if I take h cut omega common, so minus e square by twice m naught omega square. N plus n minus n minus 1. This is matching with option C. So this is a little bit complicated problem, but I think for conceptual development, you need to solve this kind of problem. Is it clear? Later on, when we will practice this question, you will find it super easy. Let's move on to the next question. Try to do this one. A constant perturbation, as shown in the figure below, acts on a particle of mass m confined in an infinite potential well between 0 and L. Okay, so we have done this case, unperturbed case, 0 to L. Now a perturbation means kind of disturbance have been added between 0 to L by 2, V naught by 2 have been added, V naught by 2 have been added, and between L by 2 to L, V naught is added. This is V naught. So you have to find out the first order correction to the ground state energy of the particle. How will you do this? Simple formula you are going to use, nothing complicated. So you have to calculate it in the ground state. So we need to write the ground state wave function. The ground state wave function is given as psi 0 is equals to square root of 2 by L sin n pi x by L. So n is 1, pi x by L. So this is the ground state. You have to find the first order correction to the ground state energy. Therefore, the first order correction to the ground state energy. Ground state means E1, right? First order correction means E1 1. This is equals to, you know the formula, psi 0, the perturbation, psi 0. This is what the formula is. Now what is the perturbation? Look, this is Actual formula is minus infinity plus infinity psi 0 star HP psi 0 dx. But here it is only extended from 0 to L. So 0 to L we can expand from 0 to L by 2, and we can write L by 2 to L. So wave function is same, square root of 2 by L sine pi x by L. So this is a real wave function. So psi 0 star and psi 0 are same. So we have 2 by L sine square pi x by L into what kind of perturbation have been used here? H naught by V naught by 2. So V naught by 2 dx. Next, L by 2 to L, what is the perturbation applied? So this one will remain. Here it is V naught. Okay. Two get cancelled. So you are left with V naught by L. So it is sine square pi x by L. So we can multiply 2 divide by 2. V naught by 2L. We can write it in this way. Zero to L by 2, 1 minus cos 2 pi x by L dx plus here V naught by L, here already 2 is there, so we can write it L by 2 to L 1 minus cos 2 pi x by L dx. So this is, you see, V naught by 2L, integration of dx is x minus cos integration is sine 2 pi x by L divided by 2 pi x by L. Integration limit goes from 0 to L by 2 plus here V naught by L, here x minus sine 2 pi x by L divided by 2 pi x by L, integration goes from L by 2 to L. So this term will be cancelled if you put L is equals to L by 2. So what you are left with from the first term, V naught by 2L into L by 2 plus V naught by L. Here also sine term will cancel if you put L and L by 2. Whatever you put, the second term is not contributing. Here it is L minus L by 2, so L by 2. So it is L by 2. So V naught by 4 plus V naught by 2. So 3 V naught by 4. So option B is the correct option. Now for the particle in a box problem, there is a short trick to solve this problem. Whenever you are given particle in a box, this kind of particle in a box type problem, and you are given some perturbation thing, then there is a short trick to calculate the first order correction in energy. It's very simple. You see, you have been given this potential well. This is L by 2, let's say. So between 0 to L by 2, V naught by 2 have been applied, and between L by 2 to L, V naught have been applied. So the rule is, the perturbation is the area, this area. Whatever perturbation you have been given, you have to calculate this area by putting L is equals to 1. You just need to put L is equals to 1. and you have to calculate the area. So what is the area of this thing? V naught by 2 into L by 2. So V naught by 4, V naught by 2 into 1 by 2. So V naught by 4. You have to put L is equals to 1. Here also L equals to 1. So this area is V naught into L by 2 means 1 by 2. V naught by 2. So the sum of it, V naught by 4 plus V naught by 2, 3 V naught by 4. In this way, simply you can calculate without calculating this much. Now perturbation is always additive here. Like the way you write energy, it is En0 plus En1 after writing the first order correction. Like if you are writing the first order correction in the ground state, so E1 is equals to E1 0 plus E1. Now if you can solve this problem quickly without calculation, with calculation you can do, without calculation yes, amazing trick. So here the perturbation is this part. So you can easily see what is the correction, V naught into L by 2. So V naught into 1 by 2, V naught by 2. So the correction confined on the box of length L. First order correction in the ground state energy. Ground state is what? So it is the formula E1 0 unperturbed plus the first order correction. Unperturbed N square pi square H cut square by twice M L square. This is the ground state energy plus perturbation. We can easily calculate V naught by 2. So obviously option D. You can calculate in the standard way. You can do it in detail. You will try it at home, okay? So take it as homework. Other than that trick, you can also cross verify it by calculating. So you need the ground state of function psi 1 square root of 2 by L sin pi x by L. The first order correction in the ground state, so E11. So this is psi 1 H prime psi 1. Here what is H prime? H prime, as you can see, this one is the perturbation. So it is perturbation have been added between 0 to L by 2. Psi 1 star H prime is V naught psi 1 dx. So this is nothing but 0 to L by 2, psi 1 star psi 1. So it is square root of 2 by L whole square sin square pi x by L, okay, V naught dx. Then you same 2 sin square theta is equals to 1 minus cos theta 2 theta, and you will calculate it. After doing some step, it will give you V naught by 2. Then E1 is the ground unperturbed part plus the perturbation. So this will become pi square H cut square by twice M L square plus the perturbation V naught by 2. That will precisely match with option D. Okay, you will try it at home. Actually, we have done this integration before. Now for this one, look, this will be applied when your constant kind of potential is applied, like this. But if you are given a sinusoidal potential, then you have to calculate actually. Here what is applied? You have this particle in a box, infinite potential box. 0 to B. Now, as you can see, the shape of the perturbation epsilon sin pi x by B. So, it is a sinusoidal. If you put B is equals to B by 2, it is 0. So, what kind of potential you have been given? This is B by 2. So, you are given potential like this. This is the perturbation. What will be the energy shift for the ground state to the first order in epsilon? Give it a try, okay? You first try, then I will tell you. The base system is the particle in a box of width B. Is it getting solved? Bottom of an infinite well potential is changed to the shape like this. What will be the energy shift for the ground state to the first order in epsilon? First of all, we need to know about the ground state wave function. So, the ground state wave function of the infinite 1D infinite potential well of width B is psi 1 square root of 2 by width means B sin n is 1 pi x by A is B here. So, pi x by P. Now, you have to calculate the energy shift to the ground state for the first order in epsilon, means therefore, the first order correction in the ground state energy. What will be this? Ground state is E1, first order correction. So, E1 1. So psi 1 HP or H prime, whatever you write, psi 1. This is the formula, right? So 0 to B, psi 1 star means square root of 2 by B sin pi x by HP is V of x, epsilon sin pi x by B, psi 1 again square root of 2 by B sin pi x by B. I am just showing you in multiple steps so that you understand it clearly. Otherwise, you can directly just write, because this is a real wave function. So you can just directly multiply. Now this will be square root of 2 by B, square root of 2 by B, so 2 by B, epsilon will come, so 2 epsilon by B will come out. Integration 0 to B. Sine square will be there and another sine, so sine cube, right? Sine cube pi x by B dx. No issue in this. So 2 epsilon by B. And now 0 to B. What is sine cube? You know the formula of sine cube theta. 3 sine theta minus 4 sine cube theta. Actually, this is sine 3 theta formula. 3 sine theta minus 4 sine cube theta. This is the formula we know. So what is sine cube theta? It is 1 by 4 times 3 sine theta minus sine 3 theta. This is what the formula looks like. So you are going to use the same formula here. One by 4 3 sine theta is pi x by B minus sine 3 pi x by B dx. So epsilon by 2b, you are getting two integration. One is from 0 to b sine pi x by b dx, another one sine 3 pi x by b dx. So what will be the integration of the first term? Epsilon by 2b, 3 sine, derivative of sine minus cos pi x by b divided by pi by b, minus here minus minus plus cos 3 pi x by b divided by 3 pi by b, 0 to b. Epsilon by 2b, this will be 3b by pi, and if you put b is equal x equals to b, so cos pi is minus 1, so this becomes 3b by plus 3b by pi. Next, if you put 0 minus minus plus, so this becomes again 3b by pi. Next, if you put b here, so it is cos 3 pi is minus 1 and b by 3 pi, so b by 3 pi, cos 0 is 1 and minus again minus b by 3 pi. This is equals to epsilon by 2b. This is, you can take this 3 pi common, LCM 3 pi, so 9b plus 9b minus b minus b, and this is equals to epsilon by 2b into 18b minus 2b, 16b by 3 pi. So b get cancelled, 2b, so 8 epsilon by 3 pi. It is matching with option C. Very interesting and good quality question. Is it clear? Can you solve this problem? Consider a particle of mass m in a one-dimensional infinite potential well of width w. V of x is given by this. The particle is subjected to the perturbation of the form w of x is equals to a epsilon delta x minus a by 2. The changes in the energy level of the particle in the first order of lambda each. Look, the problem may appear in different forms, but what do you have to stick? You have to stick with the original formula for first order energy correction. Mainly first order energy correction will be asked, sometimes second order. Okay. Here you see the changes in the energy level of the particle in the first order of lambda. Can you do this one? So particle in a box problem of width a. Okay. So from the option it is appearing that they are asking the change in energy for the nth state, okay, for all n, odd n, even n. So what is the unperturbed energy for the nth state? Unperturbed means the basic system, unperturbed particle in a box of width a. The box is of width a. So what is the unperturbed energy? N square pi square h cut square by twice m a square. What about the unperturbed wave function? Square root of 2 by a sine n pi x by a, right? Now the perturbation is given by this. So what is the changes in the energy level? Means it is talking about a first order energy correction. So the first order energy correction is in which state? Nth state, first order energy correction. So obviously this will be psi n 0 w psi n 0, right? So this is the ground state, psi n 0 is the unperturbed ground state. This is equals to sin 0 star w sin 0 dx, and this is nothing but, you see, 0 to a sin 0 square root of 2 by a sin 0 star and sin 0 same, so square sin square n pi x by a, w is given to you a epsilon delta x minus a by 2 dx. So this is nothing but a is cancelled, so 2 epsilon, okay, 2a by a, so 2 epsilon integration 0 to a sin square n pi x by a delta x minus a by 2 dx. So now you know the integration, that if x is equals to a by 2, this integration will survive, otherwise it will not. So by putting x is equals to a by 2, you get sin square n pi. Okay, 2 epsilon sin square n pi by putting x is equals to a by 2, using the properties of Dirac delta integration. So obviously when n will be odd, like if n is odd, then what will be this value? Ax equal to a by 2 na, so this will not be n pi, it will be n pi by 2. So when n is odd, pi by 2, t pi by 2, pi pi by 2, so that will be 1 square of it, so this is 2 epsilon. And when n even, means let's say 2, so pi sin pi 0. So this is matching with option C. So see how beautiful these problems are. 2 epsilon for odd n and 0 for even n. N pi by 2. I am giving you 2 homework problems. You can try it at home, similar problems. This is homework number 1. We'll discuss about the solution in the next day. Ground state wave function for the potential del v of x equals to minus delta x is given by, wave function is already given to you. You have to find if perturbation bx to the power 4 is applied, you have to find out the first order correction in energy of the ground state. Okay, this is one homework. Another homework is this. Bx to the power 4, same perturbation have been applied, but now it is applied to 1D harmonic oscillator potential, and the ground state wave function is also given, so you can easily find out the correction in the ground state energy. Will you be able to do it? So try these 2 problems at home, and we'll continue from here on the next day. Thank you guys, thank you very much for joining the session. I hope you find the session useful. Bye bye, take care, have a great day.